right, welcome to Laser Focus. My name is RJ Post and I'm with Sound and Tech. This is a series of one-on-one conversations with equine veterinary industry leaders. I like to ask three questions and we get some answers. We are joined by Dr. Bryan Stevens, a PhD. The topic today, are all lasers the same? So welcome in, doctor. Good to see you.
Thanks for having me.
Uh, Before we get into this topic, I was thinking about this over the weekend. You and I have been friends and colleagues for over 10 years now. And of course, we both work for Sound and Tech. So time flies. Um,
Indeed.
yeah. So give us a little bit of background, what you're doing for Sound now. That will give us a little bit of framework for our discussion, and then we'll jump into the questions.
Sure. Yeah, I have a PhD in physics from Vanderbilt, where I studied radiation oncology and radiobiology, basically understanding light's interaction with biological matter. Ever since I've been doing research and development on lasers, I've written the most recent book on the subject, veterinary laser therapy. And now I'm the director of product development and commercialization for Sound, heading over all of our products from digital radiography to ultrasound, CT, and both therapy and regenerative laser.
Um, I'm just because you're a PhD. I'm going to just put these on to try to keep up with you somehow. No,
We're on the same page now.
not really. But anyway, so let me jump right into the questions and thank you for your time today. So question number one, something I like to call the DNA of a laser. So, there are different specs in different boxes. And so would you please elaborate what are the important specs and functions in a laser?
Sure. Yeah, there are different knobs in a laser, whether it's in manufacturing or in settings. The most important are wavelength, pulse structure and frequency, and then output power. Those are the three big ones. Wavelength falls within the near infrared range because that's where our body are transparent to light, so that we can get things inside the body to do work. And the different tissue types and the different chromophores, things that absorb light in the body, things like the melanin in the skin, hemoglobin in our red blood cells, and the mitochondria, the powerhouses of our cells, all absorb slightly differently with different wavelengths. So the different wavelengths are used to tune to each of those things they're trying to attack or target. Pulse structure is a very important thing. Delivering light is one thing, but delivering light in different modes is quite a different thing. Whether you're using continuous wave, which means the light's always on, or you're doing it in shorter pulses with more energy per pulse, or longer pulses with different gaps in between them. So that entire pulse structure is important throughout. And then there's the power. The output power tells you the amount of energy delivered every second. And there are some ceilings to that, right? The body can only withstand a certain amount of light or energy in a given time. But the higher power within a given range determines the breadth of the clinical treatment volume as well as the clinical treatment time. You have to make sure it's feasible for your clinicians to be able to do this. If I tell you something, this is great, but you have to sit there on the horse's leg for 3 hours, that's not really a clinically feasible thing. So we use powers that bring the treatment times to a reasonable time frame. But there are some other obviously tweaks and things you can do with the parameters, but those three parameters are what I would call the fundamental parameters that determine efficacy and treatment capabilities.
So how do those just the few specs that you just brought forth,
Mhm.
how do those, or why maybe, those variations in this laser, that laser, how do those specs lead to differences in clinical outcomes? I think that might be what we're trying to put our arms around here.
Sure. So from a wavelength perspective, like I said, there's a pretty narrow gap of what we can use, right? You don't see people using mid-infrared lasers because those are surgical lasers, right? You're going to ablate the tissue, and that's not what you want to do during therapy. And then there are some visible light lasers out there, but your skin and the horse's skin are very good to protect us from that kind of light. So you don't see many of those unless you're dealing with just superficial things. You're not going to get inside the body with visible light because the skin is a barrier for that and the melanin involved there. So the near infrared is a quite narrow window that we use for therapy light. But even within that, there are some different wavelengths that are tuned to different things in the body. So different manufacturers make different decisions on what they want to target, whether it's they want to target the blood, they want to target the cells, they want to target the water inside of our bodies, which is 80% of our bodies. So these are all important things to take care of. Um, the frequencies and the pulse structure also very much are tuned to what actually absorbs in the body, right? Bone tissue is very different fundamentally than soft tissue, than connective tissue and things like that. There's different water content, there's different densities. And so the pulse structures that you use in a laser are very much tuned to a certain tissue type. And while you may be treating something, if you're treating the entire fetlock, for example, there are lots of different tissue types involved. And so using a variety of parameters within a given treatment might have better results in both the bone and the soft tissue and the connective tissues involved. And so we use between lasers, you're going to see a variety there. When it comes to power, all the same thing, right? We are thick, meaty things that we're trying to treat. And so using lower power on those things will have some benefits superficially, but if you want to get to the deeper structures and some of the harder injuries, then the higher powers are going to be are important there. And so depending on what laser is out there, whether it's there are different classes of lasers that are dedicated by power. But having an idea of what you're trying to treat is important when you're picking which laser to treat with, if that makes sense.
It totally makes sense. I get it, but it's good to put this in that context.
Sure.
So you mentioned the fetlock, right? So
Mhm.
there are a lot of things, a lot of tissue in the fetlock. Tendon and ligament tissue runs down into the foot from proximal to distal. The tendon and ligament remodeling. Talk about, if you can, expand on something big that I think we have that a lot of lasers just don't have the capability: photoacoustics, or that photomechanical shape. Talk about that, how that results in tendon and ligament remodeling. And by the way, is that unique to this technology that we have?
Sure. So photoacoustics is a hot term for sure. Laser light, when it gets in the body, does some cool things, right? And it's a very biostimulating thing. Photobiomodulation is a technical term for laser therapy, right? Forcing the body to do what it would do, only faster. Um, but photoacoustics is a different arm altogether, right? Photoacoustics means when you deliver light in a short but very energetic pulse, you can create an internal shock wave. So the light comes inside the body, gets absorbed, and that absorption creates an isotropic shock wave, a shock wave that comes out in all directions from that absorption site. Okay. And shock waves or ultrasound travels much deeper inside within tissue than light does itself. So you can reach deeper structures with these shock waves. And this is slightly different than extracorporeal shock waves, short shock waves that are created outside the body and are kind of forced and coupled inside the body. That's a different story, right? We're talking about getting light inside the body and getting the shock wave to originate and propagate throughout the tissue from there. When you do that, and so to be able to do that, you have to have very short pulses in a very energetic pulse. So it's not just about having little short pulses. You need really energetic short pulses. It's a two-termed double-sided sword there. When you do that, the extracellular matrix that surrounds all of our tissue, there are a lot of growth factors that are embedded in those. And in the normal everyday tissue, the cells will signal out to the extracellular matrix when they need some more nutrients or growth factors. And then you would come and get those back. So when you have injured tissue, that cell signaling is not happening, and therefore those growth factors are not getting to the tissue. What a shockwave can do is basically agitate that cellular matrix and extra naturally force those growth factors to seep into the tissues that need them. So when you have some dormant or necrotic tissue, you can get some what you call revitalization or regeneration where that would not have happened otherwise, right? Whether it was cut off by scar tissue or there's some fibrous tissue in there, or there's just some dormant cells that are not signaling. The inclusion of this photoacoustic therapy, getting light to produce these internal shock waves, can bring more growth factors to the cells and force them to do things they would not have done otherwise. So that's like you said, it is a very different arm than just therapy light. And yes, unique to regenerative lasers, having short enough pulses with enough energy per pulse, somewhere in the order of 500 to 1,000 millijoules per pulse is a big contributing factor to be able to cross that threshold and create those shock waves.
Yeah, well stated. And we have pretty much a good library of this research done, and white papers, and even videos, kind of like what we're doing now, giving explanation too. I mean, we don't jump into the Krebs cycle per se, but
Sure.
there's a lot of cellular interaction that you speak of. And so I invite people to go and look at that. That's my third question, but I got a text over the weekend from a vet, a user, and I'm just going to read this to you real quickly because I thought it was important to put this on. So the question is, many veterinarians like me try to explain to their clients the difference in this laser, the Smart RLT Sport RLT technology, um, as compared to others that are out there, right? And we've heard this a million times, most of which are used and purchased by lay people. From a scientific perspective, are you able to put it into one, two, three sentences that can easily be understood by the horse owner? I guess trying to say, the difference between this laser and some of the other ones that you find on eBay and whatnot.
Sure. Yeah. So at its heart, we're talking about the difference between therapy and regenerative lasers, right? Therapy lasers, like we talked about, when light gets in the body, it does very good beneficial stuff, right? Whether that light comes from the sun or comes from a laser, a handheld laser, or whatever. And even the handheld lasers are within the near infrared and visible spectrum. They're lower powered, but when they're getting in there, they're forcing the body. They're doing therapy, which we define as forcing the body to do exactly what we do, only faster and more efficiently, right? So all the very the first level pathologies that with enough nutrition and rest and exercise regimen would get better, right? So shining a laser on those kinds of things, assuming that you have enough power to reach those things, will have a benefit to the horse, right? Bringing more blood to an area, getting better oxygenation out of the blood, and forcing the cells to metabolize faster, creating more ATP to do everything they would normally do, only faster and more efficiently. Photoacoustics is a big thing. Regenerative lasers to force the body to do what it wouldn't have done with enough rest, right? When you have an internal a core lesion, for example, the body and evolution has gotten us to put a lot of collagen around it and basically cauterize it and seclude it from the rest of what might be going on, all these kind of foreign bodies. But that is the short-term fix, and nature is programmed to short-term fix, because if you're a horse, you want to make sure you get up and run as fast as you can so the lion doesn't come eat you, right? The better, more long-term fixes come from an extra-natural response. And that's what we can do with regenerative lasers. We can force these shock waves to go inside the body, generate some growth factor seepage into the cells that help them revitalize and regenerate in a way that it wouldn't otherwise. So the line in the sand there, like I said, is, would the body have fixed this on its own with enough time and rest? If the answer is yes, then there are lots of different kinds of therapeutic light that can do the trick. If the answer is no, and you need to kind of combat the natural processes there, then regenerative laser is that extra natural force. That's more than 3 sentences. I'm sorry, but
That's okay. We need to hear it, but we also have on our shelves, we have that therapy only laser.
sure.
And so
Yep.
that's probably something we're going to talk about in the future.
Sure.
For now, Dr. Stevens, thank you for being here. That's all the time we have to make it kind of short and sweet. But thank you for giving context to this important discussion. In a couple of weeks, I think I want to have you back to talk about what I call evidence of efficacy, because I think it's very important to show what you have and to match up your claims. So
Sure. I'll be back.
thank you for being here. And thank you everybody for joining us on Laser Focus. We'll see you on the next episode. Bye-bye.